All right. So far we've stuck with some theory back in, at least I've talked about the halting problem up to now, which has been pretty much theory. Today I want to take a quick detour from the book. We will go into chapter 6 today, but before we go into that, which has to do with data flow analysis, I want to talk about why are we actually doing this theoretical review. And it comes down to how do we develop programs in order to do the code analysis as well as other type of testing analysis. And currently we're looking into static code analyzers. We've done a control flow graph, but we're also going to look next into data flow graph. And these are used in order to help do code inspections. As you'll find out in this presentation, looks like by Darrell Parks, which I totally stole off the internet. It's going to go through at least some code analysis tools, why they're important, and why they're used. But really the point of this is that we've come to a point where in computer science, where we can start automating certain code inspections or certain code reviews in order to aid the programmer. But in order to do this, we really need to have a program that can actually do the inspection. So we'll go in and talk a little bit about why it's important and some tools that already exist. Real quick, I just want to mention that this presentation is about doing code analysis, static code analysis, not any type of runtime monitoring. It's not anything about profiling or debugging. It's simply what it is you have a piece of code, and another program is going to do analysis on that code and decide if you can see any problems or issues. I want to give a quick shout out to Code Complete, at least the second edition. I read the first edition, it was pretty good, so I'm sure the second edition is not bad. This part is not important. This part is. Most studies have found that inspections are cheaper than testing. This has turned out to be quite the case. If you recall earlier, testing is cheaper than having the customer tell you the error, but inspections are cheaper than having to write the test to begin with. Notice that this study in 1987 found out that code reading detected 80% more faults per hour than testing. So, someone reading the code is far more helpful than writing the test case to begin with, which in turn is far more helpful than the customer giving you the error. Another one found out it costs 6 times as much to detect design defects by using testing than by inspection. So, a unit test, while we've hopefully in the real world you've seen that testing is cheaper than having the customer find the error, what this is saying is that code inspection is even cheaper than having to write the test in the end. And this last bit, which looks like it got cut off, but slide is, it found that only 3.5 staff hours were needed to find each error to an inspection, while testing was about 15 to 25. So what can you expect? Well, it ends up being a combination of design and code inspections usually removes 70 to 85% or more of the defects in a product. That's an incredibly good result. That was back in '96, so that's even old for back then. This has probably only gotten worse due to time. So you do learn to improve their work. This is really what it comes down to, is by having some type of code review, you're helping each other out code as opposed to just siloing each other's code. Also, for design code, the inspection will take up about 10 to 15% of the project budgets and typically reduce overall project cost. This is probably the hardest thing to convince your boss, because he just wants to see something up and running and working. But unfortunately, do take at least some time. Notice you don't have to take too much time. 10 to 15% will actually overall reduce the total amount of time needed to develop the software. So yeah, you want to combine all these approaches. So a typical organization uses test-heavy defect removal approach and removes only about 85% achieves about 85% defect removal efficiency. Testing is very good. As hopefully you've seen, most large companies will have a huge battery of tests out there every time a patch goes through or something needs to be updated. And that's good. But to really get there's still a good amount of this defect removal space, so to speak, that last 15% that can be achieved either cheaper through static code analysis, or actually be found out first by code analysis of that 15%, and also a lot of that 85% can be made cheaper by static code analysis. I think this graph really hits home what he's trying to say here. This is a case study, real world. I didn't list which project it is, but the bugs remaining, let's see, after the development was 463. After QA and test, meaning they wrote a bunch of tests, it went down to 321. Not bad, decrease. $200 per fix to go from 463 down to 321, so 200 times whatever that difference is. And then to get the bugs remaining after customer fix was 194, so it took to get 194 of them is what I mean to be saying. Cost about $1,000 each. Okay. 463 shot down to 180, or 180 got knocked out. Probably is a better way of saying it. After code review for only $25. QA and test still cost 200, and customers 1,000. The point here is code review, when you integrate it into your project correctly, is actually pretty quick because you usually submit a piece of code and then someone reviews it, and then if it passes the code review, it goes into the main repository. And notice that these fixes are far cheaper than the customer, and the testing is still significantly cheaper. I mean, it's 1/5 the cost. It's pretty cheap overall, but the code review is even cheaper than that. And of course, overall cost less than half. The purpose of this, you want clean code. You want to know what the quality of the code is. Does it need to be medical level quality or, Android app quality, so to speak? Which one do you need? There are tons of different tools out here to actually do these tools. Can track suggestions, a list of available tools, code collapse, etc., etc. Google had their own tool. It's called Garrett, which I do believe is available online. Some issues with these code reviews and why we use static code analyzers. Well, first off, most people find them time consuming, even though overall they do make things cheap. It is time consuming for a developer to stop, okay, hold on, I gotta read this person's code, see what they're doing. Some people find it belittling because, after all, we're an engineer. We just spent how many years in school? Shouldn't we just be writing code and not writing test cases? It's a little lame excuse, but a lot of people do find it belittling. Boring. I have yet to meet a developer that enjoys reading other people's code right now. I'm sure one exists. Some people find it embarrassing, when you have a silly little mistake. I find that humorous, but some people are embarrassed. And yeah, this last one I think happens, rubber stamping, where people are just going through the motions. They don't actually sit down and do a full analysis of the code because they're just tired of reading code and they want to get back to their actual work. So there are automatic code analysis tools, and you could look up these. These are all pretty much, I don't think JavaDoc is one of them, but they do some type of code. Well, JavaDoc does do code analysis, just of the documentation. Find bugs, that should be straightforward. PMD, check style, depend, etc., etc. Cobertura is another good popular one. And these are all different tools in order to automate the code reviews, aka help with the code reviewer figuring out if something either needs to be done or actually just flat out reporting a problem with the code. And he's going to go through quick examples or descriptions of each one of these. So find bugs is based on the kind of idea of a bug pattern. Is a code idiom that's often error, difficult language features, or misunderstood API methods. For example, if you're in C and you call gets and you don't have a buffer, that's a straight up buffer overflow, period. It actually does a lot of static code analysis. One thing to keep in mind is it can do false warnings, not indicated real errors. In practice, the rate of false warning is less than 50%. But still, that's still pretty high. So even with find bugs, you have to keep in mind that it's going to find some errors that are actually errors. Very popular for categories, bad practices with your code, which can lead to overall code rot, and making your code worse and worse over time until you do have errors. Find correctness in your code, maybe dodgy code or experimental. Internationalization is a popular one. Malicious code and security, aka if there's obviously a security violation, you're going to have a buffer overflow or something. It's pretty good at finding that. Multi-thread correctness, that's probably pretty difficult, but there are situations where it can automatically detect, and then performance issues as well. So I can generate a report. Here's one looking, different classes, number of bugs found, errors, and missing class. Well, if it didn't find everything, you can actually click on it and go through it. Yeah, here we go. Bad practice, no serial sound, so serializable, consider declaring a serial version UID. Maybe you should add UID to it is all it's saying here. And these are other HTML project errors if you wish to go through. PMD, I think I'm going to look at this one and I'm going to stop this presentation. I've used this one before. Scans Java code and looks for potential bugs like empty try catches, dead code, suboptimal code, you're wasteful string or string buffer usage, very complicated expressions, or duplicate code. So a lot of this is pretty low-hanging, easy. It should be easy things to see, but you might as well automate it so you don't have to sit there and read it every time. And then of course it comes with a bunch of rule sets for Android all the way through different J2EE rules, JUnit, and optimization rules as well. PMD actually has a lot of tools built into it. So there's a ton of different ones. Common ones, empty catch block. All right, you have a catch block, but you don't have anything in it. You probably should check for something in there. For loops should be while. Some loops can be simplified to while loops. This makes them more concise. This is really more programming practice and making it easier to read. Notice that a lot of these really should be low-hanging fruit that someone reading the code should catch, but this just helps developers simplify the code review process. If you use Maven for your repository, some of y'all probably do, you can actually plug it in pretty quick. And then go ahead and say which rules you want inside the rule set when you're doing reporting. If you don't use Maven, just realize this is a way in your build process, once you build something, you can also have it go off and run PMD to catch to see if you have any problems with your source code as you're compiling, before you submit it. So, avoid empty catch blocks. So this is in your, looks like org-bean.java. Here are your lines where it's empty. So you probably should go in there. Avoid unused private fields. That's probably another good one. If you have an unused private field, you probably should get rid of it before someone else tries to start using it, even if it's public too. All right, and there's csci, and there's a lot of tons and tons of other tools. This one didn't give you an example of a security violation, which would be a really good example of why we need a control flow graph and a data flow graph, but hopefully you can see from the extension from these tools that you can actually give back some good analysis. So that's all I'm going to do with this presentation for now. We're going to go ahead and delve into Chapter 6 next.